In Chapter 7, we're going to be looking at arithmetic functions, such as the Euler phi function, divisor function, or sigma function. In this section, we'll start with more properties of the greatest integer function. In particular, we'll look at the p-adic valuation, so that gives us the multiplicity of a prime dividing a number n, and apply that to factorials and binomial coefficients. Then we'll define what an arithmetic function is and look at a couple examples, the divisor function and sigma function, and finally talk about multiplicative functions. So some of these properties of the greatest integer function we've already seen. Property 1, we did that. That's very elementary. Bracket x plus any integer is just bracket x plus m. The second property is a type of triangle inequality, so let's go ahead and refer to this as a triangle inequality. Although it's really different because it's saying that bracket of x plus y is sandwiched in between these two values. So it's bigger than bracket x plus bracket y, and it's less than or equal to bracket x plus bracket y plus 1. Now note, what does this really say? After all, these two numbers here are consecutive integers. So it's really saying that bracket of x plus y either equals this number on the left, or it equals this number on the right, because all three of these are whole number quantities. Property 3, we've seen that before. Property 4, this will be a homework problem. Bracket 2x minus 2 bracket x is less than or equal to 1. And then property 5, if n and a are natural numbers and we look at n divided by a, then bracket of n over a is just the number of positive integers less than or equal to n that are divisible by a. So we just want to look at properties 2 and 5 right now. Okay, so the triangle inequality. So what's going on here? Well, x and y are arbitrary real numbers. So let's say x is its integer part plus a little epsilon, where epsilon is between 0 and 1, and y is its integer part plus a delta. Right, so every real number can be written like this. And then delta is also some fractional quantity between 0 and 1. Then when I look at bracket of x plus y, what does that equal? So you would put x plus y, so you have this integer plus an epsilon, this integer plus a delta. I'll use property 1 that says these integer quantities can be pulled out of the bracket. And then I'm just left inside with epsilon plus delta. Okay, now what type of quantity is epsilon plus delta? It's going to be between 0 and 2. Strictly less than 2. So it's a real number between 0 and 2, so the bracket part has two possibilities. So we can either have bracket x plus bracket y plus 0 if epsilon plus delta is less than 1, and it's bracket x plus bracket y plus 1 if it's between 1 and 2. And that's all there is to it. So I'm telling you exactly when bracket of x plus y is the smaller number and when it is the larger number. And so it's always sandwiched in between these two values. It's actually equal to one of these two values here. Property 5, this is just the division algorithm. So by division algorithm, n is qa plus r with r strictly less than a. And then what does q represent? Well, q is the largest multiple of a less than n, so q is the number of multiples of a up to n. And so we would just want to calculate q. So this gives us that q is n minus r. So q is n over a minus r over a. And so that tells us that q is the greatest integer less than or equal to n over a, since this quantity r over a is less than 1. It's a number between 0 and 1. P-adic evaluations. So fix a prime p and let n be any non-zero integer. So we define the p-adic valuation of n, denoted nu sub p of n. So that's the Greek letter nu right there, to be the maximum power of p dividing n. So if p to the e is the multiplicity of p dividing n, that's equivalent to saying that nu sub p of n equals e. So e is the maximum power of p dividing n. Okay, so what are some elementary properties of this p-adic valuation? The first property says that nu p of a product is the sum of the different nu p values. And the second property is that nu p of a sum is greater than or equal to the minimum of nu p of m and nu p of n, with equality if they have different valuations, if nu p of m is not equal to nu p of n. Now one uses this p-adic valuation to define a new type of absolute value on the set of integers and then on the set of rational numbers, called a p-adic absolute value. We're not going to get into that right now, but that's where it leads to. So let's just prove this lemma. Part 1 is absolutely elementary. So you just say m is p to the e times, say, m1, and n is got some multiplicity, say p to the f times n1, or p doesn't divide m1 and p doesn't divide n1. Then when you take the product, you're going to have a p to the e plus f m1 n1, and so the multiplicity of p dividing the product is just the sum e plus f. So this is just trivial. Which is the multiplicity dividing m plus the multiplicity dividing n. So the real interesting property is this second property right here. Why is nu p of a sum at least the minimum? Okay, so once again we just start by writing m and n in their canonical forms. So say m is p to the e times some odd number m1. n is p to the f times some odd number n1, not odd numbers, for some m1, n1 not divisible by p. So some canonical representations like this, and then we look at m plus n. So one of these two exponents is bigger than the other, so without loss of generality, let's assume that e is less than or equal to f. So I can always assume one of those two is the bigger one. Then I've got a p to the e I can factor out of this equation. So I pull it off, leaving me with an m1 here and a p to the f minus e n1, which implies in particular that p to the e is a divisor of m plus n. And that means the largest power of p, so this means nu sub p means the largest power of p dividing m plus n must be at least as large as e, because p to the e divides that number. Aha! What have we just said here? E is the minimum of e and f. That was my Willog assumption. And e and f are the multiplicities dividing m and n. That's nu pm, and this is nu pn. So we've got the first inequality established, and now for the second part, what's going on there? With equality if they have distinct values. So if nu pm does not equal nu pn, then under our same Willog, we would have that e is strictly less than f. So f minus e is a positive number, at least one, which means that p is not going to be a divisor of m1 plus p to the f minus e n1. Why is that? Well, p is a divisor of this term, but p doesn't divide this term. So if p was a divisor of this sum, then it must be a divisor of m1. So we say else p divides m1, a contradiction. So what do we conclude here? Therefore, if p is not a divisor of this, then coming back up to star, we have the exact multiplicity of p dividing m plus n. So by star, nu p m plus n equals e, which is the minimum of e and f, giving us the equality. Okay, next let's look at the multiplicity of a prime dividing a factorial symbol. And there's a cute little theorem here. So fix a prime p and let n be any positive integer. Then the multiplicity of p dividing n factorial is the sum, as I goes from 1 to infinity, of n divided by p to the I power with a square bracket, so the greatest integer part of that. And the first thing you want to note is that this is really just a finite sum. So why is that? So it stops when p to the I is bigger than n. All of these terms become 0 at that point. So there's really only log to the base p of n terms in that sum. So don't think of it as an infinite sum. That's just a convenient notation. And the proof, in words, it's very straightforward. So we have n factorial means this. P times 2 times 1. And so if I want to count the multiplicity of p dividing n factorial, I want to add up the multiplicities of p in each one of these numbers from 1 to n. Well, some of those numbers are divisible by p. And how many? So n over p numbers, this is by the first theorem, is the number of values divisible by p. So the number of values from 1 to n that are divisible by p, bracket n over p squared, is the number of values divisible by p squared, and so on. So in general, n over p to the I is the number of values divisible by p to the I power. So if I want to get the total multiplicity, I add up how many numbers are divisible by p, and that gives us a contribution of 1 to each of those numbers. And then I count up how many numbers are divisible by p squared, and I get another contribution from those numbers. And so we just sum up all of these values to get the total multiplicity. Okay, so that's the idea of where this formula is coming from. And it really is a complete proof. But if you're asking, well, how do I actually write this down in a rigorous manner? There's a device mathematicians sometimes use to formalize these type of arguments. It's making use of what we call a characteristic function. So let me show you how I might do it for this problem. So for any natural number I, I'll define a function chi sub I on the natural numbers to be 1 if p to the I is a divisor of k, and 0 if p to the I is not a divisor of k. So chi I is a characteristic function that identifies which natural numbers are divisible by p to the ith power. And then we note, if I take a natural number k and I want to look at its multiplicity, so nu p of k, that would be the sum, as I goes from 1 to infinity, of chi I of k. So we're asking lots of different questions here. We first ask, is k divisible by p? And if so, this will give us a contribution of 1. And then we ask, is k divisible by p squared? And if so, I get another contribution of 1. And again, this is a finite sum. So you just keep adding up 1 plus 1 plus 1 plus 1 plus 1. And how many times? You'd add it up e times if p to the e is the multiplicity dividing k. So then, going back to our theorem, if I want to calculate nu p of n factorial, so what is that? That's the sum, as k goes from 1 to n, of the multiplicity of p dividing k. So I want to add up all those multiplicities. What is its power in 1, its power in 2, its power in 3, and so on, all the way up to n. So that's just following from the multiplicative property of the p-adic valuation. then I'll use this formula here. So I just insert that new p of k is this sum right here. And again, it's just a finite sum. So what do mathematicians like to do when we see double sums? Well, we instinctively want to just swap the order, and you don't have to worry about convergence here because it is just a finite sum. And then look at this inner sum right now. What does that equal? Well, this will equal 1 whenever k is divisible by p to the I power. And so we're just counting how many numbers from 1 to n are divisible by p to the I power. Now we know what that is. The number of integers from 1 to n divisible by p to the I is just bracket n over p to the I. And that gives us a nice rigorous proof without even having to introduce any sentences describing it. Okay, let's apply this result to find the multiplicity of p dividing factorials, and binomial coefficients. So what I want to prove is a well-known result. For any positive integers m less than or equal to n, the binomial coefficient n over m is an integer. And if you've had any combinatorics, well, you'll say, well, of course, we know that this is a whole number because it's the number of ways of choosing m objects from a collection of n objects. But what we want to do here is just think of this as a symbol defined in terms of factorials and ask, how do you use just basic divisibility properties to prove that that symbol is an integer? And more generally in part 2, if you have k integers, k positive integers, whose sum is n, then I claim that the product of their factorials is a divisor of n factorial. And just note that part 1 is just the special case of part 2. It's just the case when k equals 2, right? Because in part 1, what's the definition of n over m? It's n factorial divided by m factorial times n minus m factorial. And so think of this as an a1 times an a2, where a1 is m and a2 is n minus m. Sum of two non-negative integers or positive integers adding up to n. Okay, so let's turn to the proof of 2. How do I show that the product of these factorials is a divisor of n factorial? Well, here's the trick. If I want to show one integer as a divisor of another integer, what I do is think of the prime factorizations of these two numbers and look at each of the prime powers. So if I can show that the prime multiplicity of p in the left side is less than or equal to its multiplicity in the right side, that will show that the left-hand number is a divisor of the right-hand number. So let's fix p to be any prime. We must show that the multiplicity of p dividing the left side here is at most the multiplicity of p dividing the right side. If I can do that for every prime, that means this number on the left is a divisor of the number on the right. Okay, so let's calculate it. What is nu p on the left-hand side? a1 factorial, ak factorial. By the product property, the multiplicity of a product is the sum of the multiplicities. So I equals 1 to k of nu p ai factorial. And then I use the formula from our last theorem. So nu p of ai factorial, I sum, and I better use a j right now, of bracket ai over p to the j. So that's the multiplicity of p dividing a sub I factorial. And then remember, these are finite sums, and I can then switch the order of summation. J equals 1 to infinity. Sigma I equals 1 to k. Bracket ai over p to the j. Aha. So write it like that. And now we use the triangle inequality. So the triangle inequality says if we have a sum of two things like that, and this is what we're looking at, we've got k objects we're adding up, this is less than or equal to bracket x plus y. And so this is less than or equal, and then we do induction to get the same thing would hold true if I'm adding up k different brackets. And so I'm adding up k different quantities here. And so that would be bracket as I sum these quantities inside. So you'd have a1 over p to the j plus a2 over p to the j, like this. Now, what does that add up to? You got the same denominator in every term, and so that's just a1 plus a2 plus ak over p to the j. But by assumption is what? We come back to this assumption here. The sum of the a sub i's add up to n, so that's just bracket n over p to the j. And that's exactly our formula for nu p of n factorial. QED. You might try that just from scratch. Think about this binomial coefficient, even in part 1 here. Look at this symbol here, and see if you can just go back to definition of divisibility and prove that that denominator is a divisor of the numerator. It's a challenge. You might try to do that and see if you can convince yourself of that. Okay, arithmetic functions. So an arithmetic function is just any function defined on the natural numbers. I mean, it doesn't have to be going into the complex numbers, but all of the functions we're dealing with are going to be doing that. So a couple standard examples. The divisor function just counts the number of positive divisors of n. The sigma function denotes the number of the sum of the positive divisors. And more generally, we can talk about sigma k of n to denote the sum of the kth powers of the divisors of n. So in sigma notation, I would write the tau function like this. So this means the sum over the distinct positive divisors. So that's just a convention to mean D is a positive divisor of n. Sigma of n is the sum over the distinct positive divisors of D. And sigma k of n is the sum over the distinct positive divisors of d to the k power. Okay, it turns out that all of these are going to be multiplicative functions. And we saw this idea come up with the Euler-Phi function. So what's a multiplicative function? It just means that f of a times b is f of a times f of b whenever a and b are relatively prime. If it's true for all values of a and b that we have this multiplicative property, we'll call f totally multiplicative. So some functions are totally multiplicative. So note, if f is multiplicative, then it's determined by its values and prime powers. So if n is a prime power factorization like this, p1 to the e1 through pk to the ek, then since the distinct prime powers are pairwise relatively prime, the multiplicative property, using induction, tells us that f of n is the product of the f values over these distinct relatively prime factors. Conversely, if f is an arithmetic function satisfying equation 1 for all positive integers, then f is multiplicative. Indeed, if m and n are, suppose m and n are relatively prime, so they have prime factorizations with distinct primes. So say m is product of pi to the ei's, and n is some product of qj's to the ej's, where the pi's are all different from the qj's. And you look at f of m. So f of m, if 1 is true, would be the product of the f of pi to the ei's. F of n would be the product of f of qj's to the ej's. And f of mn is what? Well, mn, its prime power factorization is the product of the pi to the ei's times the product of the qj to the ej's. Remember, these are all distinct primes. And so it would just be this product first times this product second. So you get it, that f is multiplicative. Now in general, for multiplicative functions, we do not have f of a prime power to equal f of p raised to the power. The problem being that p is not relatively prime to itself. So this type of property only holds when we have a totally multiplicative function. So lots of multiplicative functions are not totally multiplicative. So as an example, let's revisit the tau, sigma, and phi functions. So the divisor function tau is multiplicative. So we saw that if n has a prime power factorization, p1 to the e1 times pk to the ek, then tau of n is just the product of ei plus 1. I going from 1 to k, and that is in fact the product, I going from 1 to k, of the tau value at each of the prime powers. So it has that type of multiplicative property. The sum of the divisors, the sigma function, is also multiplicative. So we'll prove that next time in a rigorous manner. But let me see if I can just convince you with an example. So let's suppose that I want to look at sigma of two different, just a p1 to the e1, p to the e times q to the f, say, where p and q are distinct primes. So I want to find all of the divisors of this product and add them up. Well, let's start by looking at sigma of p to the e. So this is just add up all of its divisors. Then sigma of q to the f means add up all of its divisors. Look what you get when you multiply these out. Sigma p to the e times sigma q to the f is this sum times this sum. And when we use the distributive property and gather together all of these terms, the typical term in this product, you'll take one of these guys where I is going from 1 to e, and you'll take one of these guys where j is going from 1 to f, and it'd be a p to the ith power times a q to the jth power. So this is what a typical term in that product looks like. But look what we're adding up here. This represents a typical divisor of p to the e times q to the f. And so we are simply adding up all of the divisors of p to the e, q to the f. And so we're getting the multiplicative property. Sigma of a product is the product of the sigmas. And then earlier we saw that the Euler-Phi function was multiplicative. That followed from the Chinese remainder theorem, CRT, and the fact that the group of units mod mn was isomorphic to the group of units. Well, I think we were using G, weren't we? The group of units mod mn is the same as the group of units mod m cross the group of units mod n.